everyone, it's Judy Warner. Welcome back to this week's Ecosystem Podcast. We're so happy you can join us. Today I speak with John Coonrod, who is a technical marketing manager at Rogers Corporation. Today we're going to talk about how you can navigate the pitfalls that exist between your designs and modeling and simulation versus what you end up getting back from your fabricator. There's lots of hidden pitfalls there, and we're going to start unpacking that for you. This is especially problematic as we go into mmWave designs. So I'm going to put all kinds of technical resources for you in the show notes. I want to say thank you to all of our sponsors and welcome our brand new sponsor, Summit Interconnect Technologies. Without these sponsors, this podcast is not possible. So make sure you check out the show notes and enjoy this conversation with John Coonrod of Rogers. Hi, John. Thanks so much for joining us again today. I'm so glad to have you again.
Hi, Judy. Good to see you again.
Well, last time we did this podcast, we touched a little bit on a subject, but barely. And so I wanted to get you back and talk about kind of a blind spot, right, when it comes to RF microwave and mmWave boards. And so why don't we just jump right in and we'll start talking about the things that the blind spots, both from fabricator side and particularly the engineering side, is how at fabrication, the performance of the board, what an engineer models and simulates does not match the board they get back.
Yep, I see that a lot.
And I saw it a lot too. So let's dig in.
Yeah, so as part of my role at Rogers, I am in a technical service role for our customers that are doing design. So actually at Rogers, I'll tell you real quick, we have two different groups that do technical support. One group that does technical support for the fabricator and helps them deal with circuit fabrication issues. And then another group that deals with the RF designers or high-speed digital designers, the electrical designers, I guess. And that's the group that I'm really part of. And there's probably never a week go by, maybe several times in a week, where someone doesn't ask me, why does this circuit not work the way that the simulation said? And there's a lot of obviously really good simulation software, electromagnetic modeling software out there. And I think it's really, my point of view is I think it's kind of a disconnect, and it's no one's fault. It's not the designer's fault because they go through years of school for electrical stuff, and they don't, in electrical and academia, they don't have time to talk about how to build a circuit board and all the different aspects of it. And then the circuit fabricators, they come from a different background and they know how to build boards extremely well, but they may not know all the things that the electrical guys are looking for. And I say guys, gals, sorry. But anyway, there's kind of a disconnect there. And then when they actually start talking to each other, the light bulb comes on and go, oh, I didn't simulate that, or I didn't think of it that way. And gosh, I run into that a bunch.
Well, way back when I was working at Transline, who is one of the sponsors of the podcast now, I would run into that all the time because I was like a technical sales manager there, and they'd like, man, what I modeled and simulate, Judy, doesn't look anything like your board. And then we'd go look at the Traveler and everything we did, and we're like, we did everything to spec. And so it took me a bit of treasure hunting. So I think this will be, you and I both had that experience, you far more than I have, but I found a few gems, and I'm sure having those multiple conversations a week, hopefully we'll build some bridges. And one thing I want to say right here, if depends on also how those boards are getting purchased, right? So if it goes through a buyer, great. But so many times these days, right, it goes through, the board gets ordered turnkey through the EMS shop, right? And then they build the board. So the fabricator sometimes isn't even in the conversation.
Right. Yep.
Which creates another level of disconnect. So, okay. So let's start talking about, why there's these gaps.
Right. Yeah, I'll tell you, one of the most common things I run into is the effects of final plated finish. And what happens is the RF designer, a lot of times they either don't know about the final finish having an effect, or if they do know about it, they may assume that it's a much lower effect or doesn't have as much effect as they would assume. or
Yep.
they're just thinking that it's not going to have much effect because of what they know about it. But in reality, the final plated finish can make a really big difference. And it's a funny one because it's frequency related. So as frequency goes up, the skin depth gets thinner. And that means you get kind of a composite conductivity between copper, nickel, gold for a gold plating. And at a low frequency, you're using a good amount of metal there. But at higher frequency, you're using less copper, more nickel, and some gold.
Right.
And then if you happen to hit the right frequency where you're using a lot of nickel and gold, and the nickel varies in thickness, which it naturally does, then you can actually see differences. And I've seen this several times in base stations that were operating around 2 gigahertz or less, some of the older technology. And it was
Wow.
just so funny. We got a circuit in one time and we could not figure out what it was, why they had so much variation from circuit to circuit. And finally, we figured out it was the thickness of the nickel that was varying, and nickel thickness does have normal variation. And it just so happened the skin depth happened to be just right to when it was on the thin side, you got a very different response than the thick side for the nickel being thick
Right.
and thin. And then there's other things too. So like when you go up into higher frequencies, when the like millimeter wave, when the skin depth is really really thin, then the final plated finish makes a big difference. And if engineers have been working with final plated finish at lower frequencies, they think, well, it's not going to make that big a difference when they go to this other application that's higher frequency. And then they learn the hard way that it really does. So there's multiple things when it comes up to final plated finish.
So it's been a while since I worked directly for a fabricator, but has anything in the last 10 years sort of addressed that? We always knew that nickel is
Right?
lossy,
Yep.
right? And
Right.
that exact thing you're talking about, which gets far worse now, you're telling me at millimeter
Oh
wave.
yeah.
And then we were talking about, well, let's not use nickel, which
Right.
engineers think, yeah, let's just not use it. Just plate the gold directly to the copper, which
Yeah.
doesn't work, right?
Yeah.
You can't
Yeah.
do
There's
that.
issues.
Yeah. And then it's like, well, maybe it's palladium or maybe it's
Right.
like, has any other solutions come along like in the last 10 years?
Yeah, and I've been working with a lot of the suppliers of these final plated finishes, and they have come up with different options, and it's really a juggling act. So I'm most interested in the RF side of things. So we did find EPIG. Do
Yeah.
you remember what that stands for?
Wait,
Electrospalladium
is it
immersion?
EPIG? Is it or any pig?
No, it's EPIG.
No,
Well, any
no
pig.
nickel.
Right, right. I looked
Any
at any
pig
pig
still
too,
has
but
nickel.
right. And EPIG doesn't have
It's
nickel. It's electrospalladium uh,
electrolysis palladium
immersion gold.
immersion gold.
Yeah, I think that's right. So anyway,
So it's
that
palladium.
yeah. So that looks really good for RF, even out to millimeter wave frequencies. But that's not the only issue they have to deal with. So sometimes they have to deal with wire bonding, and that wire bond's different than ENIG and all
I
these
see.
other things. And then long-term storage sometimes is an issue, and just a lot of different things that they worry about for final plated finish. My favorite finish, I guess, would be immersion silver for RF. But the problem is, over time, as you know, immersion silver looks pretty bad over time. It oxidizes and
Yeah,
looks terrible. But you know, it's funny though,
it
is I did
does.
a study a few years ago on an edge coupled filter, which should be a worst case scenario, where you have circuit features that are they're together and they're edge coupled, and they're edge coupling through the
Mm.
final plated finishes too. So they're very sensitive to final plated finishes. And with immersion silver, after 4 years of aging, the silver was really
Oh,
heavily oxidized, looked terrible. And I tested it, and it performed exactly the way it did when it was brand new, when it looked all nice and shiny and clean. And so that
mm.
oxides for silver doesn't look good, and it probably does cause other issues for, I don't know, if wire bonding or whatever it may be. But for losses, it doesn't cause an issue with loss. It doesn't look good, but it really is no problem with losses.
That's really interesting because I remember that issue and, people were thinking that oxidation would not only look good, but degrade over time, but you're
Yeah.
saying, "No, it
No,
doesn't."
actually, I think the reason why, I'll just tell you real quick, sorry. The reason why I think it's kind of interesting is if you look at silver oxide, it's not much difference in conductivity than silver is. And that's why the
Oh,
silver oxide might look terrible, but the conductivity isn't enough difference to really change it much. Whereas if you look at copper and copper oxides, there's a big difference there. Yeah.
and then I was always like, "Well, just throw some clear solder mask on it."
Yeah, there you go.
It's like, "No," but then there's bonding issues, there's
Yeah,
then there's the effects of the solder mask,
right, right.
so
Yep.
again, I always feel bad when we start talking about stuff like this, John, because I think, oh, our listeners are like, great subject. Tell me what to do. And it's
Right.
like, it
Well,
depends.
exactly. Yeah, I always hated that, but
it
it's true. It depends on so many things. Now, Eneg, I think, is a fantastic finish for everything that you could think of, except that you have to account for more losses, and you also have to account for more variation because the nickel thickness is varying. But Eneg's great for wire bonding. It's been known for years and years, so
I
it's a
know.
very well established process. But unfortunately,
Have you written anything on this as far as like
right?
trade-offs or is there anything you personally have done to
Yeah,
sort of
I've tried to. It's a pretty big subject, but I've written a couple of
yeah,
things, a couple of articles on it, and that's available on our tech support hub, which is good, so people can read that.
okay.
But it's really a juggling act, and it depends, as you said. It's because
It's like one of those what are those charts called? I'm completely having a mind lapse where if this then that,
oh yeah,
right?
yeah,
I feel like we need to make one of those,
right.
except I think it'd be so
It
wild
would be
because
crazy,
it's all about trade-offs.
right?
But if you have something published like on the tech support hub,
Hmm.
and send me those links,
Oh,
I'll put them in the show notes
right.
here.
Yeah, be happy
Because
to.
again, I'm always like, well, this is interesting. We're talking about that, and we're giving exactly nobody any clear answers, right?
Right.
But at least we're serving up like, here's the problem.
Right. Yeah, you need to be mindful of this. And if the designer knows that the thickness of the nickel is going to vary plus or minus something, they can put that in the simulation. But simulating final plated finish is not an easy thing. It's kind of a headache, and that's why a lot
Mm.
of times the designers try not to do that. But well, when you get the higher frequency, you really have to.
Well, okay. What other things? Let's go
Oh,
on to something else that I used to tell engineers, I'm like, give me your files. I go, there's only about 100 ways we could screw up your performance
yeah,
over here.
it's true.
So right. So let's go on to two. We won't hit 100, but I know you
Yeah.
have the recurring ones that you see week after
Right,
week.
and one of the more recurring ones is more of a material issue, and that's copper surface roughness. And some of the simulation models can account for copper surface roughness and some cannot. And that gets a little
Mhm.
confusing there. And also, that's another topic that someone might think that, when I was operating at 2 gigahertz, that was not a problem at all. I could turn roughness on and off, and I'd see a little difference, but not much. But if you do that with a skin depth that's really thin at 60 gigahertz, you'll see a huge difference because at that high frequency with really thin skin depth, the majority of the RF current's using that roughened surface. And as that roughened
Yeah.
surface varies, because it's not a perfect surface, it's going to vary roughness from batch to batch of copper. That's what will make a difference from batch to batch in performance of the same design of circuits being built in larger volume. So that's another
So
one.
when it hits so when it hits that rough and it has to be rough
Hmm.
or it won't adhere to the laminate, right?
True.
So
Yeah.
when you hit that edge like that,
Right.
does it lengthen the effective trace length or what
Oh,
happens or it just gets
oh,
noisy?
yeah,
Like
yeah.
what effect does it
Yeah,
have?
that's the problem with what I do sometimes. I'm so deep in this, I don't think about, explaining it. So, really, for copper roughness, it's related to skin depth. So, if you think of a cross sectional view of copper, it's really thick, and only the very bottom is roughened. At lower frequencies, the RF current is using the whole conductor. And then as you get to higher and higher frequencies, you use thinner and thinner until it's just using the roughened area. And when the signal's used in the roughened area, one thing that's obvious is it will slow down. So as the wave propagates down the circuit on a roughened conductor, it's going to be slower than a wave on the exact same circuit that's
Mm,
smoother. So
mhm.
the roughened surface kind of, it actually gives you a longer path, even though that's not a real good way to think about it. But it's an
Okay, well,
intuitive way to think about it. So, a rougher surface gives a longer path, and yeah, so it slows down
okay.
and also gives more conductor loss effects. So the conductor losses get exaggerated.
Okay.
So the slowing down part affects the like propagation delay. So if you have two circuits exactly the same, rough versus smooth copper, the one with the smooth copper is going to have faster propagation. One with the rougher copper, slower propagation. And then that also affects phase too. So phase velocity and phase angle related to that is also affected. So there's a whole bunch of things that this roughened copper affects, but it's frequency dependent. So if you're doing this down around 600 megahertz, you may not even notice it. But at 60 gigahertz, you'll definitely see a difference in roughness.
I see.
Yeah. So does that kind of make sense?
That completely makes
Okay, good.
sense. But I thought I'd ask that again
Sure.
because it's not always clear,
Yeah, I hear
especially to civilians like me.
you.
All right, what else? I know there's
Oh,
more.
yeah, there's a lot
And
more.
I think is one I'm thinking of right now has to do with the way that board fabricators etch,
Oh, yeah.
right?
Right. Trapezoidal
Traces.
effects
So
and things like that. Oh, yeah, that's a big deal. And what's funny is the trapezoidal effects, I guess to explain it real quick, is most of the modeling software is going to assume you have rectangular conductors in your cross-sectional view of a model. In reality, if you take microsections of the same circuit being ran in high volume production, you'll see that sometimes it's kind of rectangular, sometimes it's trapezoidal, and there's some variation from very trapezoidal to rectangular, and it can be trapezoidal the other direction too, depending on how the circuit is being
if
made.
you over
Yeah,
etched,
yeah.
right?
So
Yeah,
that
yeah.
trapezoidal effect for a microstrip, where you just have one single conductor, that's not that big of a deal. It does have some effect, but not much. But where the trapezoidal effects come into play the most is when you have coupled conductors, like differential pair, where you have two
Mm.
conductors side by
Yeah.
side and they're coupling. If they're tall, square, rectangular walls, you get a lot of coupling fields. But if they're slanted away from each other, you don't have that much coupling fields. And because of that, you really do get a difference in coupling and whatever this coupling would affect in the circuit. So trapezoidal effects is a big deal, and mostly I see that at millimeter wave. And the reason why is as you go up in frequency, a lot of the RF designers will transition from a simple microstrip circuit, which is just simply a signal conductor on top, ground plane on the bottom, to a ground equiplanar waveguide where you have ground signal ground on top and ground on the bottom. And that helps a lot of things when you go up in the millimeter wave range, but it's more sensitive to trapezoidal effects because the ground signal ground, they're coupled together with these electric fields. And if they're angled away from each other, you get something different than when they're more rectangular, you have more fields. So at lower frequency,
Interesting.
you may not see it much, but at millimeter wave frequency, you're going to definitely see differences due to that. And the trapezoidal effect, well, go
Well,
ahead. I could talk on.
no, no, I mean, no, I love this subject. Again, I'm always sort of listening with the ears of people who might be hearing our
Oh, yeah, sure.
conversation and just like throwing the book across the room and just going, forget it. You
Yeah.
know, I'm doomed. But I always feel like I want to give them some
Yeah,
hope.
sure.
But to go back to the trapezoidal
Hmm.
effect at the board fabricator, right? You print, you
Right,
etch, and there's different types of
right.
etchants, right? And you etch, depending on how thick that
Oh,
copper
right.
is, will impact, right?
Hmm.
So the dwell time, why it gets that trapezoidal effect
Right,
is when it's dwelling in the etcher,
right.
in the etchant, it hits the surface first and then goes
Hmm.
down. And so you're trying to get that effective width,
Right.
by the
Yeah,
way, that is allowed for within a tolerance because it's an imperfect process,
exactly. Right.
right? And but we get like a plus or minus tolerance
Right,
at a
right.
board shop,
Yep.
and we're like, we're good. We
Right,
met the
exactly.
IPC spec. But
Exactly.
the poor RF engineers over there going, I modeled this with perfectly straight sides. And all of
Exactly.
this is sort of the fabricator is blind to well, some depends. I'm blind to the effects that fabrication
Hmm.
have on performance. And then engineer is blind to trapezoidal effects because of
Right,
their modeling or their simulation. And it's
right.
just creates this perfect storm, which is why I'm interested in additive technology
Oh,
because RF
true.
engineers have made, we don't care if it's trapezoid, but we just want it to be the same trapezoid every time. And I'm like,
Exactly.
uh,
It's not how it works.
our technology is ancient and it varies from lot to lot
That's right.
and depends on the day, how old the etchant is, blah, blah,
Yeah,
blah. But for a
exactly.
fabricator, it's still within
Mhm.
IPC specs. So we're like, we're golden,
Exactly.
right? And so it's tricky. And I
Right.
love the idea of additive because you can get a cleaner trace geometry. that could be modeled
Right.
and can be repeatable.
Right.
So
True.
that's why I've kept my eyes, and I think you've kept your eyes on that
Oh yeah,
too.
absolutely. Very interesting.
Yeah.
But yeah,
Yeah.
the thing I would recommend for RF engineers would be to do sensitivity testing with their simulations. In other words, talk to the fabricator, find out what their tolerance is for the conductor width and also trapezoidal, and then try to make models that represent worst case and best case of that, and then see what the performance is as you vary across a range of conductor widths and trapezoidal shapes according to what the fabricator tells it could be. So if they can do that,
There's a
yeah,
solution, a helpful solution.
exactly.
Good.
So if
That's
they can do
good.
that, then they're set. But it's not a simple
Yeah.
model to do with most of them to draw these trapezoidal effects. You actually have to manually go in and do it with a lot of the software, as opposed to assuming it's rectangular. You just press a button, off you go. So
Right.
it causes the designer to do a lot more work, and but it's very much worth it. It will tell you the difference.
Okay. Well, I feel better that we came to
Yeah,
at
I felt
least
like I had to say
some
something.
way. Yeah, that's good. Let's give them some hope,
Yeah,
John.
exactly.
Okay.
Well, I'll give
What
them a little more
else?
hope too, real quick, is the coupling effects like differential pair and other type of couple effects that I was talking about with the trapezoidal shapes making a big difference. That's true when it's tightly coupled. So if you have a very tight space in the coupling, that's very true. But the wider the space gets, the less that trapezoidal variation matters. So normally what I tell
Mm,
people to do whenever they're doing the
okay.
design, make sure you design it to where you have the least amount of coupling to be effective, and don't try to give it the really tight coupling that should be really good for a lot of
I
things.
see.
But if you open it up to where you have less coupling, then the coupled circuit will be less sensitive to trapezoidal effects, less sensitive to final plated finish, less sensitive to a lot of things.
Which is a good point, right? You and I have both seen a tendency like you said, I always say everybody's innocent
It's
here.
true.
Like it's nobody's
But
fault. It's
yeah,
just it's like a unfortunate
yeah,
events, right? A series of unfortunate
right.
events. That's what we should call this
That's
podcast.
what it is.
Um, right?
I agree.
So it's right. And it's like, well, again, designers sometimes tend to over design thinking tighter
Right,
coupling's good. If some is good,
right,
more is
right.
better. And so I think what you said is helpful, and maybe, I don't know, you'd have to tell me, sort of
Yeah.
counterintuitive to what
Yeah.
they might be
Right.
thinking.
No, I
So,
agree with you 100% because when engineers starting to work with millimeter wave, they have issues at millimeter wave that they don't at lower frequency. Like they have more radiation loss, so more energy being radiated off the circuit. They have more spurious modes, or basically wave modes that can interfere with the mode that you do want. They have unwanted resonances. They have all these different things that grounded coplanar waveguide can be really good at minimizing or eliminating. So yeah, tighter coupling is a good thing for that, but tighter coupling makes the circuit much more sensitive to a lot of circuit fabrication variations, and it's normal variations. It's not like they're doing anything wrong. It's just normal variations in making the circuit.
okay, we won't dig into it now. I know you have a lot of good resource on the Technical Support Hub, which
Sure.
is free, but let's make sure we circle back
Mm-hmm.
after this and, work together to get all those
Okay. Yeah,
links.
we'll do.
Because yeah, it's like I remember doing a talk once. And it was a free talk at
Mm-hmm.
PCB West, and I was doing it. This guy,
Oh yeah.
Michael
Yep.
Ingham, right? And we were talking about it, and I'm like, I know, let's do a talk at PCB West about navigating the pitfalls of RF design and
Uh,
fabrication. Thinking, well, we could all see this problem. And I thought, oh, this will be a cute little free talk. He'll talk about the
yeah.
designer side and then I'll talk about the
Right.
fabrication side. And won't that be great? Over 100 people showed up and there's people lining the walls. And I was like, uh-oh.
Yep.
So I was thinking about this earlier, like, John, we need to do that talk or record it or
That's a good idea.
something, or you need to, you
That's a good
know,
idea.
do it with Dale
Yeah.
Doyle, who had 18 years of
Oh yeah.
fabrication. Anyways, just to,
Yep.
squirrel. Okay.
Yep.
All right. What
Oh,
else? And then we want to talk about millimeter
sure.
wave, but
Um,
What else can fabricators, or what are those
Oh, there's
pitfalls?
several, but the big ones we talked about. But there are issues with drilling that comes up from time to time, and drilling holes in a circuit, obviously, to get connections from one layer to the other. Depending on what kind of circuit design
Mm-hmm.
is, the drill tolerance can come into play to give more variation than you'd expect. And the drill tolerance is really tight. So if you
Hmm.
drill a hole, one hole to another, that tolerance is plus or minus a mil, sometimes even better than that. But at millimeter wave frequencies, plus or minus a mil can be a difference of 1.5 gigahertz in frequency difference. It could be a big difference. So yeah, it's
Oh
always
my
something.
word.
So the problem is at millimeter wave frequencies, the wavelength is so very very small that these very small anomalies that are not detected at lower frequency, they are detected at higher frequency. And going back to this grounded coplanar waveguide structure, that's really good for millimeter wave, theoretically, for the minimizing the things you don't want. That also has to have plated through holes in it because you got ground signal ground on top that has these grounds on top have to via the ground on the bottom. And if those vias move in location, it actually does have a little bit of effect on it's a long story, but it has an effect on different things, and it will not match the simulation exactly. And again, at lower frequency, that little difference, you'd never even know it. But at higher frequency, where you have smaller wavelength and everything's more sensitive, believe it or not, a plus or minus a mil will do it. You can get a pretty big difference. I think the worst case. Oh, go ahead.
Which is well, and like at a fabricator, plus
Yeah,
or
I
minus a
know.
mil. I mean, we're doing laser drilling these
Oh
days,
yeah.
which helps a lot. But some people are still using mechanical drills.
Yep.
I'm just like,
Yeah.
how do we do this?
Yeah.
It's tricky. It's not just like it's not IC level where
Right.
no big deal,
Right.
right?
Right.
It's
That's
hard
true.
again because the technology at a board shop
Oh
has
yeah.
evolved a lot, but
Yeah.
not enough. And the board effects end up having a huge
Yeah. True.
okay, I'm going to ask you
Sure.
about one thing that I don't think was on your
No, that's all right. Go ahead.
topic list, but I wanted to touch on it before we go a little deeper into the
Sure.
millimeter wave, the blind spots of
Hmm.
millimeter wave that you're starting to see all over
Right.
the place right now. The other thing I've talked to people about is about the
Hmm.
pre-preg and about
Right.
skew and about the type of glass
Right.
you use related. And again, I think that's another it's getting
Yeah.
more attention now, I think, the
Right.
skew. So why don't you talk about that a
Sure.
little bit?
It's not just prepreg. Prepreg's part of the issue, but also the laminate as well. But yeah, it usually probably shows up more in prepreg than
Okay.
anything else. But there's different
Okay.
glass out there. The glass has been used for years and years is e-glass, and it's usually an open weave. So if you zoom in really close to it, you'll see you have bundles of glass and open areas and bundles, and I can't really do that, but you get some kind of a checker pattern, kind of, sort of.
Like
But
yes, like a
right,
basket weave. That's how I
yeah,
picture it, but
yeah.
it's not exactly, but
So what
yeah.
happens is when you get the higher and higher frequency, that little opening that's only between these glass weaves, that little opening is only anywhere from 8 mils to 20 mils. It's not huge. And at low frequency, the wave is just so long across that little opening, it never even detects it. But a higher frequency at really small waves, then that little opening is a good portion of that wave trying to go across there. And now you get these fields that will hit a area with no glass, an area with glass, no glass, glass, and that gives you kind of a zipper type of pattern for impedance, where you have low impedance, high impedance, low impedance, high impedance, and that causes problems. One of them being skew for digital or propagation in general. It's going to be slower actually because you don't have a nice clean wave now. You're actually being disturbed as you move along. I guess that's a good way to say it. So that's one
Yeah.
issue.
And then
Yeah,
they've
go ahead.
talked yeah, and then I've heard, the importance of when it becomes an issue that there's been a lot of data gathered on that it's better to I mean, there's
Oh
various
yeah,
ways to do it. Some have
right,
pivoted the
exactly.
chip,
Yep,
like, for
yeah,
I don't know,
yeah,
45
right,
degrees or something like that, but the other way is to use
exactly,
spread glass so it closes up
right,
those holes, and then it propagates more
exactly.
cleanly.
Yep, I
So
did a paper on that too, so
okay.
I'll send you a link for that. And it's mostly geared toward
Okay,
millimeter wave
awesome.
because high speed digital has been looking at this glass weave effect for years and years, and they know about it. And the RF people,
Yes.
they were not that
Mm-hmm.
much aware of it. And once you start getting up a millimeter wave range, they started
Okay.
seeing differences because of the glass. So I wrote a paper on that, and I'll give you the link to that.
Great. Okay. I'm
Okay.
writing myself a note too. Um, all right, let's go into
Sure.
millimeter wave because this seems to be an area that you're talking to
Oh
engineers,
yeah.
RF engineers,
Yeah,
more
definitely.
and more and more because it does not act the same as RF
Right.
and microwave. And so, again, yay, more
Exactly.
pitfalls to navigate.
Yeah,
Just
it's true.
kidding. But I know that you really have a passion to
Right.
get this information out and to raise awareness, which is, why I love having you on
Yeah.
to, let people know what's going on. So let's go into
Okay.
some of that, some of those.
Yeah.
I mean, we've touched on some of it
Right.
as we've been
Yeah.
talking, right? Um, but just first, overall, let's just give us
Mhm.
some context about why you're
Oh yeah.
seeing it
True.
all the time now and why the rules of thumb in RF and microwave have completely
Yeah,
changed or
yeah,
don't
that's all
apply.
true. I think what really happened, and I'm no expert in the topic here, but I think what happened with the millimeter wave push nowadays is that the chip industry finally figured out, well, it's been several years ago, that they figured out how to make chips operate very consistently at millimeter wave. I think prior to that, many years ago, there was a lot of attempts for that, but there were some issues with either high volume manufacturing of the chips or something else. But it seems like maybe 10 years ago, something like that, the chip manufacturers started bringing more and more millimeter wave chips to the market. And as they got better and better at the technology, that opens up a huge amount of new applications because the band spectrum is pretty tied up at lower frequencies. But a lot of the higher frequencies, millimeter wave, there was actually a lot of open spectrum, you might say, that hasn't been used or could be used. And I think, again, I'm no expert on this part of it, but I think that's why I'm seeing more and more millimeter wave applications. And man, I see a lot of new applications that are
I
millimeter wave.
see.
So it's basically given the designers these new tools to operate at much higher frequency, and you get some benefits out of that. But you also have a lot more headaches too.
Which is
Yeah,
exciting on one hand, again, but then it's like,
yeah,
whew, now there's a new set
right,
of and what I think so interesting, I had dinner with a couple of like powerhouse, a power amp
right.
designer last night and because these are the kind of
Yeah, that's
people I
cool.
hang out with. And another one that I know, no,
Yeah,
they're so great. We had a lovely dinner, but we were talking about, they all work at the
right.
chip level, right? And I was talking to them, and I feel like they're so far above my pay grade technologically,
Yeah.
but they teach me a lot. And I was telling them that everybody I'm talking about is saying that their problem now consistently
Oh,
is
yeah.
board effects. And this
Right,
is what we're talking about. Like, great, the
right.
chips work there, and
True.
then it hits the board, and and
I
it's like,
agree.
okay, we need to
Right.
educate right there, right? And you have really been on the front lines of that. So there's the pain point, and we've touched on some of again, it doesn't matter for RF and microwave frequencies. Then you go to millimeter, and it
Right.
exposes right
Definitely.
vulnerabilities and things. One thing we
Hmm.
didn't touch on was about the performance issue as it relates
Oh,
to
that's a big deal.
thermal, right? To
Right.
operating temps. So why don't you
Sure.
unpack that a little bit?
That's another thing I've done some papers on, and I'll have to send you a link to that as well. But every
Okay.
material has something called TCDK, and TCDK is thermal coefficient of dielectric constant. And what that means is that every material, as you heat it up and cool it, will change properties. Of course, everyone thinks of CTE, it expands as you heat, contracts when it cools. Well, you also
Right.
have dielectric constant changing with temperature, and you also have dissipation factor changing with temperature. So if a engineer actually
Mm,
evaluates a board and fine tunes it in a lab, and then they put it out in the field where it goes through wide swings of temperature, they see big differences in performance,
I
and
see.
that's one of those
Mm.
issues I deal with pretty often too. So TCDK is really important, and some high frequency materials are much better than others. So we formulate many of our high frequency materials to make sure they're flat for that. So as you heat them up, the change in dielectric constant is very little. But I've seen this from many, many times on 77 gigahertz automotive radar, where they will do testing in the lab or something, then they put it in a
Uh,
unit and go drive around. The unit itself actually heats up some, but then you also have the outdoor effects and the sun shining on it and everything. And then as it heats up, it changes performance, and then they have issues. So that,
or you drive to work in Chandler,
yeah,
Arizona
true.
in the summer,
Yeah.
right?
Yeah, it's crazy hot here in the summer. But
Yeah,
anyway, that heating and
exactly.
cooling will make a difference on the circuit board and how it performs, unless, again, the RF designer is aware of it and they do models and simulations to figure out, okay, the decay could go up this much when it's hot, and decay could go down that much when it's cold, and then do some models to see what difference in decay causes, what effect.
Right. And I think it comes back to that, like, just having
Yeah,
situation awareness so
exactly.
your models are good.
Oh,
Like, you
yeah,
can model for it, but you can
exactly.
if you don't know it's there, and you don't know it totally worked at my
Right,
microwave level frequency, but now I've gone to millimeter, and all of a sudden it's
right.
like, "What's happening?" Right? I don't
Yep.
think we touched on, which you and I have talked about sort of
Uh-huh.
offline before, because 'cause we've both seen it in the past, is particulate millimeter wave. Now I'd like to hear you talk about the effect of this, is the final copper thickness variation.
Oh, yeah. That That is a big deal with some designs, and I also got a paper on this one too that I'll send you. But
Okay.
the reason why is because the copper thickness does vary from circuit to circuit in manufacturing, and I think most of the circuit fabricators are pretty good at controlling that, to be honest. But it does have some tolerance. And again, at microwave frequencies, differences like that may not be detected, but at millimeter wave frequencies, definitely. And also, along with that, is usually at millimeter wave frequencies, they want to do something to minimize the unwanted resonances and things, and that's where these coupled features come in. So if it's coupled, that also is going to throw in another variable in there as well. So if it's coupled and the copper's plated thick, now you got really tall sidewalls coupling, and if it's not plated thick and it's thinner, you have less sidewalls coupling, which
Mm,
means in one case you have more fields in error, in another case you have less fields in error. So that means the decay of what the wave sees is going to be lower when you have more fields in error. And when it's more thin copper, you have less fields in error, and it's going to be higher decay actually, because error is very low decay, about one.
right,
So,
exactly.
and again, at microwave frequencies, you can see the effect, but it's not as dramatic as at millimeter wave frequencies. And that's some of the problem is when a designer goes to these higher frequencies, they want to get rid of these other problems. And one way to do that is this grounded coplanar waveguide or coupled features in general. And that copper thickness variation that's normal from batch to batch, that can make
Mhm.
a difference in RF performance.
And again, from a board fabricator's, it's like, "Oh, well, this is within spec.
Right.
It's within tolerance."
And
And, yeah.
also again, the sensitivity testing that I said before is they can run models on that as long as they talk to the fabricator and know what to expect for the difference in copper height and copper thickness. They can run a model with the thin copper, run a model with the thick copper, and see what the difference is, and try to make sure the circuit operates within that range.
Now what's the effect, say, um, when you do multiple, like, say if you're using buried and blind vias,
Hmm.
and so sequential lamination that has to go through multiple
Right.
plating excursions, like,
Yeah, that's
um,
tricky. Some of these 77 gigahertz automotive radar I've been working with, they do that. They have multiple plating because of microVias or different things they're doing, how they're building the circuit. And
yeah.
I've seen some of the designers put specifications on the circuit fabricator to hold the overall copper thickness to a pretty tight spec, and it's not easy to do when you do these build-up
Mhm.
structures. So that's something that the designer really has to work closely with the fabricator on to understand that. But,
Yeah.
yeah,
And again, it sounds like such a, uh, I don't know, with how complicated these designs are, especially for our microwave, millimeter wave,
yeah.
you know, devices and, systems. It's like, it seems like the least intuitive thing to, like, go talk to your fabricator. It's
I know.
really, really important, and
It's
I've
really
been singing that
important.
song for years, but then I feel like,
Yep.
God, I am aware of that, and you probably are more
I am.
so. It's like, boy, go talk to my fabricator.
Right.
Usually I design the board, I might give it, different ways. If I'm doing prototype, I might be really tightly coupled to the process, or
Right.
I might just design it, give it to the buyer,
Oh,
and
true.
they'll go do whatever they do with it, and it's
Right.
like off. And so you don't, you may or you may not talk to your fabricator. But anyways,
Right.
I think if you do have those conversations, it sounds like a kind of silly, mundane thing to do, but I've heard
Oh,
it over
it's,
and over again by people who have actually done that.
yep. It's
Like Rick
very valuable.
Hartley,
Oh,
who
yeah.
designed really complex RF systems for L3. Finally, he
Exactly.
just said, I'm going to go. And he went in deep, and it completely impacted how he
Right.
designed. So can't say it enough. I know it sounds like a simple solution, you know.
Oh, it's
All
true,
right.
though.
Well, I'm
I
super
agree.
excited to pass on those resources that you
Sure.
have. And also, um, before I let you go, I wanted to give a shout out to um, recently we got a new sponsor who I know
Mhm.
you know, John, which is Summit Interconnect
Oh, yeah,
Technologies.
sure.
And
Yep.
so they are now a sponsor of the ecosystem. And I do this strategically
Oh,
for a
good.
reason, right? Because
Mhm.
they provide good, Jerry Partita and some of
Mhm.
their internal subject matter experts put good resources out there to talk
Right.
about this. And I'll see if I can pull some of that. And also translating technology, which is how I learned this
Oh,
crazy
yeah.
RF fabrication side. They're also a sponsor, and
Great.
they're really good at quick turn,
Oh,
talk
yeah.
to your fabricator. They're
Yep.
more at the prototype quick turn. And Summit is more, they'll do prototypes, but more. So if you need a fabricator to talk to, I'd recommend those two. They're both quite capable, and I picked them for a reason. So,
No, absolutely.
um, and then John and all his resources. So, for our
Sure.
listeners, there's some little beacons of hope to tap into, and then, yeah. So,
Right.
and then also our other sponsors. I'm trying to build this ecosystem so you can go grab like
Yeah,
stuff
sure.
from Keysight, right,
Right.
about modeling, and they
Absolutely.
have some good stuff there. Matt
Oh, yeah.
Ozales was on the podcast, right? And he was
Mhm.
talking about he used to design our um, power amplifiers for
Right.
years, right?
Uh-huh.
And then he went to work for Keysight, and he's
Right.
working on the modeling and simulation side.
Oh,
And
good.
because he's been on both ends,
Yeah.
he kind of sees the whole thing. So
That's
he does a
perfect.
lot of YouTube and stuff. So
Right.
we'll pack the show notes with all this good
Good.
content where you can go tap into the ecosystem and get some good stuff. But start with John's stuff,
Okay.
um, identifying the blind spots, and then you
Yeah.
can go find the other good stuff. Is there anything else you wanted to touch on? I feel like we've covered it all, but
Yeah, I think we hit the highlights anyway. So I think I'm okay.
okay, good. John, is Rogers going to be at PCB West? And I think they're in October this year.
Yes, we are. I'm going to be presenting there. I'll be presenting
Okay.
something.
All right. Well, I'll hunt that down, because if you're listening to this podcast and you're able to get up to Santa Clara and kind of Northern California, that's coming up, and
Yeah,
that's
it's a good
another
show.
great conference. It's a great
Yep.
show. John usually presents there, and
Yep.
Rogers, I'm sure, has a booth there.
Yep.
So that's
Mhm.
another good way you can tap into
Sure.
some fabricators on the show floor and Rogers, and then get
True.
some good technical education. So,
Right.
well, John, thank you so much. I always
Oh, thank
love
you.
these phone calls with you, and
Yep. Thank you.
giving our audience some resources and some hope. And so thank you so much for joining us again.
My pleasure. Sure.
For our audience, thanks so much for joining us today. We love doing this for you. Make sure you go like and subscribe wherever you're finding the Ecosystem podcast, and come over to the-ecosystem.com, join our community. I'll hope to rope John into an online community where you can continue asking him questions, like through Discord or something. I'm working on that right now. So thanks very much for joining us today. Thank you to all our sponsors for helping make this podcast and conversation possible. We will see you next week. Until then, remember to always stay connected to the ecosystem.